Hi, and welcome to our discussion, our continuing discussion on anemometry. Specifically, we're going to talk about different types of wind speed measurements, and we're looking at speed sensors right now. And this PowerPoint presentation is going to spend time discussing hot wire anemometry. This is done, of course, through a heated wire. The wire is heated anywhere from 300 to 1,000 degrees Celsius. Wires are typically made of either platinum or tungsten, and they're very small. There are two types of hot wire anemometers. There's either the constant temperature type hot wire anemometer or the constant current. The constant temperature hot wire anemometer allows the current to vary to maintain the temperature of the wire, whereas the constant current hot wire anemometer allows the temperature, of course, of the hot wire to vary, and as a result, the resistance of the wire varies. So as the wind blows by the hot wire, there's convection that's occurring. Convection meaning that energy is being lost to the air from the wire because of the velocity of the fluid. And it is a function of the velocity of the fluid. In this case, the fluid we're talking about is air. So we're going to look at a hot wire that's surrounded by air. Air is blowing by this hot wire. And we're going to assume that the velocity of the wind is constant, so therefore there's got to be a balance between the energy that's lost by the hot wire and the energy that's being produced to keep it at a given temperature. So here's our equation, and you're not going to have to calculate this, but do any calculations, but this is just basic, just to give you an idea of what's going on here. In other words, there's current that's flowing into the hot wire. The hot wire has a certain resistance, so it heats up to a certain temperature. So the electrical power that's going in, of course, which is the current I, and also the resistance RW, so that's the electrical power, is lost by the wind speed. So we have on the right-hand side the temperature of the wire and the temperature of the fluid. Of course, the temperature of the wire is going to drop, but it's of course heated to much greater temperature than the temperature of the air or, of course, the fluid. So the heat that's lost depends upon that temperature difference. Also, a heat transfer coefficient, that's H. We're going to look at that here in a little bit. And then also the area of the wire. How big is that wire? So the resistance of the wire is also a function of temperature. As the temperature increases, the resistance increases. As the temperature decreases, the resistance decreases. And the heat transfer coefficient, well, of course, that depends upon the wind speed and also a couple other of coefficients. And these are coefficients that we determine from calibration. So here's our equations. Yikes. The one on the top left is the power balance. The one on the top right is heat transfer coefficient. We're going to mash those two together and rearrange the equation a little bit so that we solve for the velocity of the wind raised to, of course, the c power you see there. Also, we'll stick into the equation the resistance of the wire as a function of temperature, so we'll put that in there. And at the bottom, what you see is we have an equation that relates the wind speed to the resistance of the wire, the current, and also the temperature and the area of the wire. So we'll rearrange that, raise it to the 1 over c, and that gives us the wind velocity. So this is how we figure out the velocity of the fluid going by the hot wire. It's a function, of course, of the resistance, the current, the temperature of the wire, the temperature of the air, and also the area of the wire, as well as a few other constants. So with a constant temperature hot wire anemometer, of course, you try and maintain the temperature of the hot wire the same. However, the wind is blowing by it. So as the wind blows by the hot wire, the temperature of the hot wire wants to drop. You have to figure out how much it dropped, and that way you figure out how much current to put in to maintain the temperature. So the current that you put towards the wire is basically the velocity. It's related to or calibrated to the velocity of the wind. Constant temperature hot wire anemometers, of course, require also the ambient temperature, in other words, the still air temperature, not just the temperature of the wire. So you have to take the difference between those two. And as we said before, current determines the fluid velocity. We measure the current and we figure out what from that the fluid velocity. A constant current hot wire anemometer works a little bit differently. You just continue sending the same current into the wire, produces a certain amount of resistance as the fluid flows by the wire, the temperature drops and the resistance drops. So from that, you can figure out the speed or velocity of the wind based upon the resistance. Measure the resistance, and you can figure out the velocity, the fluid velocity. So, there's these two different types, the constant current and constant temperature hot wire anemometers. Seems like the constant temperature hot wire anemometers are more common than the constant current. Constant temperature, remember once again, try and keep the temperature constant by putting in the right amount of current to keep the temperature the same regardless of the wind speed. So some pluses and minuses of hot wire anemometers. Of course, they have a very low threshold wind speed, meaning that the distance constant is only a few centimeters, and the wind speeds can measure a few centimeters per second. So they measure very, very low wind speeds. Typically, hot wire anemometers are made of, the wire itself is made of either platinum or tungsten, so they can achieve very high temperatures. They're usually very small, only about 1 millimeter in length, and they're very, very small type anemometers. Another type of anemometer that uses heating and ventilation is the hot film, and it's very similar to a hot wire, except instead of using a wire, they use some sort of film as a conducting material that heats up, and you can measure the resistance of that film. So here's a couple examples. Sometimes they use a Pyrex wedge right at the leading edge. They coat it with platinum, a platinum film, and then they run a current through that. That is heated, and of course the ventilation or the wind blowing by that film causes a drop in temperature, and the current is increased to maintain the temperature. So that's your constant temperature hot film anemometer. They also, instead of using a wedge, you may see a glass rod that's on the leading edge of some non-conducting material that also serves the same function. Here's a picture from NASA showing a hot film on a airfoil, and they use hot film anemometers, of course, to measure fluid flows in wind tunnels. Very common to see these in the aerospace industry. So here's your pluses and minuses of hot wire anemometers. The pluses, of course, they have great spatial resolution. Also very high frequency response on the order of 10,000 times per second. It can get a value of wind speed. So they're very good for measuring turbulence. But the cons is that since it's such a very small wire, it can break very easily. It's fragile. If you use these on an aircraft when you're flying through rain or flying through hail, they'll break frequently. Of course, they need to be recalibrated, and then of course they're costly. Just picking up a hot wire anemometer to be used in a lab is typically anywhere from $600 to $1,000 or more. So that's an overview of hot wire anemometers, and we'll continue a conversation on anemometers in another PowerPoint presentation.